The speed of flight is compared to the speed of sound, where the speed of sound is Mach 1. Supersonic flight is faster than Mach 1, and hypersonic flight is faster than Mach 5. Supersonic and hypersonic passenger aircraft present many similar problems in their design. However, hypersonic aircraft experience these issues to a greater degree, such as experiencing higher temperatures and requiring more power. There are many benefits of hypersonic travel. Here are 4 of the greatest benefits. The first is in business. Hypersonic travel will increase ease of business relationships in a global market, even allowing you to fly halfway across the world for a business meeting and return home the same day. The second benefit is in emergency response. Hypersonic travel would allow for rapid deployment of resources and personnel in emergency situations, such as natural disasters or humanitarian crises. It could also allow for rapid mass evacuation of populated areas. The third benefit of hypersonic travel is lower cost spaceflight. By utilizing the altitude and speed of hypersonic travel, satellite companies can utilize lower prices to put their product in orbit. The final benefit we will discuss is research and development. Developing hypersonic flight lowers the barrier for real-world data on hypersonic speeds that can lead to improvements in understanding and future designs.
Why don't we have hypersonic jets already? Well, for a hypersonic vehicle to be economically viable, it must be able to access the largest proportion of the available market. This means establishing many far-reaching flight paths to service the needs of as many people as possible. The attempts of the British and the French resulted in the Concorde, a marvel of engineering in its own right. However, where Concorde fell short was its ability to access much of the market, keeping to its niche flight path between New York and Paris or London. The reason for this was twofold. Concorde lacked the range to cross the Pacific in a single flight, removing the US-Asia market. It produced too loud of a sonic boom to fly over land, removing anything other than a transatlantic flight path. These shortcomings did not allow the Concorde to tap the market effectively, making it an expensive operation funded mostly by the British and French governments before its eventual retirement. In this video, we will be discussing the sonic boom intensity issue. The extensive overpressure from the shock wave of supersonic and hypersonic flights disrupts populations on the ground. If a supersonic or hypersonic vehicle produces a sonic boom that would be too disruptive, it will be required to fly much slower, likely subsonically. Hypersonic vehicles have low lift-to-drag ratios, since these jets will be designed to operate most effectively at high speeds. This makes them incredibly inefficient at slower speeds, using a lot of fuel to stay airborne and overcome the higher drag compared to vehicles designed to operate subsonically. This means land routes become much more expensive subsonic flights, which use a lot of extra fuel. This is both economically and environmentally inviable.
Here are our proposed solutions. The design features of an effective hypersonic vehicle that would likely reduce the intensity of shockwaves are as follows. The vehicle would have a very long and narrow airframe, utilizing a fineness ratio far larger than its subsonic counterparts. The fineness ratio is the measurement of the length of a shape to its width, often used as a measurement for fuselages. Maximizing the fineness ratio while maintaining passenger comfort, along with a long, pointy nose reminiscent of the X-59 design, would maintain a minimized frontal footprint of the vehicle and increase the length along which overpressure occurs. This reduces the perceived loudness of the shockwave, which is known as PLDB. The vehicle would also have swept-back wings to reduce the effects of wave drag and increase the surface area of the wing inside the shockwave. The engines would likely be packaged closer to the body of the plane, which limits their effect on shock intensity. This is due to them already being inside the disturbed air of the shockwave, which reduces their disruption on the airflow. As the air has also slowed down, the leading shockwave helps with the increased pressurization needed for engine operation. Different speeds, altitudes, and conditions require different outer mold-like characteristics to reduce the shock intensity, so investing in morphing leading edges and fuselage components is important. Morphing leading edges allow the shape of the vehicle to change slightly so that the profile interacting with the air can best take advantage of the oncoming flow. This will allow the vehicle to effectively operate in a wider variety of conditions and balance the sometimes competing effects of drag efficiency and sonic boom intensity. Furthermore, flying at higher altitudes will reduce the perceived loudness in decibels of the shockwave at ground level. Balancing all of these factors will allow for the absolute minimization of the shock intensity, allowing for a more diverse range of flight paths and market availabilities.
Created using Powtoon.